So recently, we published papers of ASIC to stabilize the deep reconstruction network. So here, I would like to give some theoretical interpretations. So first of all, let me give some background information. So in about 2020, one paper published on PNAS. So basically, three kind of instabilities have been reported. So the authors believe that these kind of instabilities cannot be, I don't know what happens. It looks like it goes directly. Okay. So, the authors believe that that kind of instability cannot be easily deal with. So here, I think the major issue is that, yeah. So for the first instabilities, basically, the well-trained neural network is vulnerable to the patients. That is, when they are very close to input, so the output may have significant difference. So for this kind of instability, so it means the false positive in clinical applications. So regarding the second instability, so some small features in the input may be missing in the output. For example, there are some letter-like structures that can be missed, so in the output. So for this kind of instability, it can result in false negative result. Well, regarding the third instability, so that means some overload result. So this demonstrate that with some increased number of projections or data set, so the network performance actually become worse. Actually, from the point of view of the commercial reconstruction, and we have modeled the performance should be increased. So therefore, it doesn't make sense. Well, to solve the problem, so we published two papers. Our work called analytic, compressive, iterative framework. That's ASIC. Next one, let me give more detail about ASIC. So here is the principle. To understand why we would need ASIC, so we need to answer the question: why one well-trained neural network usually is unstable to the inverse problem, particularly for the tomographic reconstruction? So here, basically, the simple answer is that the neural network actually is lack of kernel awareness. So, briefly speaking, so that means the neural network has no prior knowledge or information about the solution space. So here, with the tomographic reconstruction problem as an example, here we can assume AF equals B. Here is a image model. Well, usually it is a pose problem. So for this kind of pose problem, well, in the summation, the solution can be decomposed in two parts. One is F0I and F0V. So this F0I, we call it invisible component. Let us say this component is in the null space. So it satisfies AF0I is 0. Let us say this component cannot be measured by system metric. Well, meanwhile, we have second component. We call it a visible component. So visible component is in the visible space. So basically, AF0V equals B0. Let us say what we reconstructed may be just the visible component. We usually cannot reconstruct the invisible component. So in the deep learning based method, so basically we collect a set of the samples or ground truths. So for the ground truth, definitely each image has two components. One is visible, the other is invisible. So because of existing of the invisible component, so while the deep neural network actually just want to fit kind of function from the input to the output. So therefore, when we have two real measurement, so they are maybe very close in the measurement space, but after the output, so while the visible component may be close, but the invisible component may have bigger difference. So because of this kind of big difference of the invisible component, so we can say the result may be significantly different in the output. That is the phenomenon of the instability. So, well, compared to the reconstruction network, so CS actually is stable because CS has a kernel awareness. So here is an example. So this image is not sparse, and we give some sparse transform. This is a discrete Green transform. So it becomes sparse. So because CS knows the solution has kind of sparse information. So we use the sparsity information, it can be guaranteed that exact and stable result can be reproduced. So this is CS. Well, now we already know one deep reconstruction network is not stable because of lack the kernel awareness. On the other hand, CS has kernel awareness. We make next thing. So can the neural network combine with CS to make it stable? So yes. So well, this is basically what we call integration scheme. Well, here is our answer. So we call it ASIC. That is an analytic, compressive, iterative debricker. So basically, if we have the data set input, okay, we have reconstruction network. First of all, we may reconstruct some initial image. So after we have the initial image, this image may be not good enough. So we can let it pass through the safe component to refine the image. After refinement, so we will perform some forward projection, then compare it with the data set. So we have the data residue. The data residue maybe not zero. So well, we let it again pass through the reconstruction network. So this output actually is to be the image increment. So we combine image increment to the previous image, so update current image, then pass through the set component. This procedure can be repeated again. Then we have the kind of iterative scheme. So well, with kind of iterative scheme, finally, we can find the solution in the space of data prior, the space of sparsity, and the space of the solution for data fidelity. So therefore, we can have a better result. This is a basic principle. Well, the question is that for this kind of ASIC scheme, is it kind of ad hoc design or not? So after I say it's not kind of ad hoc design, so we have theoretical interpretations. So next one, let me give some details. Well, here we have data model. T star equal to AF star plus E. Here is system magic. F actually is an image object to be reconstructed. So we assume, so the image is sparse after the sparse transform H. For the network, it will train to solve the problem AF equal B. That is A fed P, approximately to P. That is the network fed can be viewed as the input problem for the measurement. Well, here to solve the problem, we introduce the residue mechanism. Let us say we give the residue P as intermediate variables. So our task is that we want to find the residue magnitude P in the image F simultaneously. To solve the problem, we need to analyze the variables. Okay, here we have three spaces. One is the measurement space. In the measurement space, we have the input data set. We also have the radial data P. In the image space, we have F. So from the measurement space to the image space, we can use network effect. We have the sparse space of the image, so we can perform sparse transform H. From the sparse space of the image, we can get the data measurement. So here we can perform inverse sparse transform, then perform the measurement A, that is a forward projection. Well, in the three kind of space, we want to find the P, find the F. Well, in the image domain, so this is image F. So when it F, we just need perform sparse transform, then get the measurement. So they have radial P. So this plug together, we can have the input to the network. So the output of network with the different F, it is as small as possible. So this is first one. There's a data conjoint in the image space. Then in the measurement space, so we should have the initial projection. Then we have forward projection of the F. We have also radial P. So the initial input minus the forward projection of F minus the residual should be as small as possible. This will be approaching 0. Meanwhile, in the measurement space, P actually is very small. It should be very small. We need to minimize our know. So in this sparse space, we know 8 should be sparse. We need to minimize our know. So as you can see, in the three space, we have 1, 2, 3, 3, 4 components. So our object can be solved by minimizing this loss function. So we have two variables, P and F. Using what we call block coordinate descent method. So we can just optimize the R function. We have one iterative solution. So has a P cap plus 1, so the F cap plus 1. So basically, there is an update of the rich function, this update of the image. So back to our ASA framework here. For the refined image, this component we can read as cap. That is the current update of the image. So this one, which are denoted as P cap plus 1, is updated data set of the residual. So, well, now compare with this framework and our iteration. So you can say here, for projection of the current image. So compare with the data set. So we have data residual. This exactly correspond to the update of the projected residual. So then we just have fed P cap plus 1. That's it, we let the data residual into the reconstruct network file. So this component correspond to this part. Then F cap plus this one, this is computation of previous result with the image increment. This correspond to this component. Then we have H. H just perform the sparse transform. So here S, the option is a soft threshold filtering. Basically, it is to perform the CS. And this one, H-1, it perform the inverse sparse transform. So H-1 as H, they come together, correspond to the CS component here. So that's why we have this kind of result. Well, for this kind of iterative solution, well, the one important thing that it kind of iteration converge. So, well, to analyze the convergence, so we have what we call BRAN property. Basically, meaning that the L1 norm of the reconstruct image, so have the strong images. Let us say, in the reconstruct image, so the ground truth should dominate the result. So the object, the artifacts to be smaller than the ground truth. So basically, in the result, the ratio between the L1 norm, L2 norm of the artifact with the ground truth is to be smaller one. This is the assumption of our BRAN property. So well, for the BRAN property, so here we have done some numerical simulation. So we basically use the adversarial attack to generate samples. So well, we did a lot of experiment for several representative networks. So we found the maximum ratio is about 0.58. That is, it's still smaller than 1. That means our BRAN property is satisfied. So with this kind of BRAN property, so we proved that the iterative solution actually convert to the ground truth upon one error term. The error term actually is bounded by the noise level. So this makes sense. Well, this is a BRAN property. Next one, let me discuss some related issues. The first one is that, so currently many people publish papers. So they have the unrolled network. So, well, I would like to say ACID actually has a significant difference with the unrolled network. First of all, for the unrolled network, well, because usually we need to train small network. So it needs a lot of memories. So therefore, for that case, unrolled network can only have small subnets. So for ACID, it can have very big net. This is the first thing. Second thing is that image size, due to the limitation of the memory, image size for unrolled work usually is very small. So maybe 256, but 250 is kind of some related large now. So for the ACID, it can be very large. The third one, so ACID has set component. So unrolled network has no set component. Actually, also unrolled network can be viewed as a whole. So we can use ACID to improve the stability of the unrolled network. For example, here we did some experiment. So we show the ACID can further improve the model-based deep learning method. So, well, this is the orange one. This is use ACID. Next one. So when we ask, so as a whole, for the ACID, it's still stable to the adversarial attack. Actually, we have just implement kind of a complicated algorithm to generate adversarial attacks to the whole ACID system. So our result shows that so the whole ACID actually is stable related to this kind of samples. Last one, I would like to say in the current ACID scheme, okay, we assume the intermediate variable. Actually, you can have different intermediate variable. Meanwhile, when we just use the using the coordinate descent algorithm, we can change the orders of variables. So in this case, maybe we can have different iterative solutions. So different iterative solution actually can have different architecture of the ACID. So for example, here we have the ACID2. So meanwhile, we may have a lot of applications. For different application, we can have some special design for the network and also for the set component. That is, using the ACID as a framework, we can have a lot of applications. So we can apply it to cardiac activity, can apply it to the condensity. So I will not give more information. So last one, I would like to say, for the computation of the iteration and the neural network. So obviously it can include the instability. So except our result, I also see some other result. For example, yesterday I was not here, but Dr. Wang bring the attention to me. So Dr. Jagaba gave the talk. So in the talk, he just have the multiple learning method. So with the iterative algorithm. So his result is all very preliminary. It's similar to our result. So this show the memory efficient with convergency and robotics. So this is very nice. So, well, this is last one. Then I would like to thank my collaborators and the co-authors. So your comment and the page are welcome.
Questions for our speaker? I had a question. I like your use of adversarial attacks. Did you also think about, or is there a value in considering, say, like pathologies that are, weren't present in your training data that could also kind of, test, how well it could, handle very different images?
Yeah, currently for the adversarial attack, so we just using some model-based loss function, we find the maximum difference.
Yes.
So for that kind of technology meanings, so we may just need the input from clinical physicians. They may give out some advice. So which way is best? I think currently are not clear which one has clinical meanings for the attack. But definitely we need the input from clinical physicians, and they give us more advice. Which kind of way we can just limit the attack to some structures. I think it is more useful.
Thanks. Questions? Okay. Well, let's thank our speaker now.